As a silly goose myself, bird migration is fascinating. How do they know exactly where to go and successfully complete their journeys over distances as long as 90,000 kilometers, in the case of the Arctic Tern? The answer has confused scientists for ages. We know that, much like some old-timey sea captain, birds use celestial signs to navigate. They also use smell. Both of these processes are well understood through studying their eyes and beaks. There's one more important sense at play here, though. Through experiments done by Wolfgang Wachtelsko in the 1960s, we also know that birds have some kind of internal compass attuned to Earth's magnetic field. How can they sense this? Untangling this phenomenon lies in a quantum quality called entanglement. Here's the gist of it for today's purposes. The ducks are stand-in for particles today, and they make up what's called a radical pair. Not those kinds of radicals, but chemical radicals, meaning the atom or atoms that make up the particle have either one extra or one less electron than usual, making them unstable and either slightly positive or slightly negative. In radical pairs, these aren't just two separate free radicals, but rather entangled ones, meaning that if you make a measurement on one or change it, it changes the other. These ducks are best friends, and where one goes, you know the other is sure to follow. No matter what I do to one, it inevitably changes the other. The way these ducks face, so to speak, also models another quantum property key to migration: spin. Both ducks facing the same way, or having the same spin, is called parallel spin, and they are in the triplet state. If both ducks have opposite spins, they have anti-parallel spin, and are in the singlet state. How does this relate to birds again? As it turns out, within the eye of the bird, in the retina specifically, there are proteins called cryptochromes that contain two molecules, TRP and FAD. FAD is a yellow molecule, meaning that it absorbs blue light, which energizes the molecule and causes an electron to jump from the TRP to the FAD. This creates a positive and a negative, a radical pair. This radical pair then undergoes what's called a singlet-triplet waltz, where the spins of these molecules switch rapidly. The probability of which state the molecules are more often in is dependent on Earth's magnetic field, as each spin has its own tiny magnetic pole. So it's hypothesized that through this process, birds can perceive where they are in orientation to Earth's magnetic field, as it is stronger near both of the poles. Although it's not entirely proven yet, as we can't record exactly what goes on in birds' eyes, the cryptochromes have been replicated in labs and demonstrated this process. Additionally, we also know that birds' sense of magnetic fields is partially light-dependent, strongly supporting this current theory. But why should you care? Cryptochromes are not only found in birds. In fact, they were first discovered in plants and have also been found in fish. This research of linking quantum qualities to biological organisms could help greater our understanding of how flora and fauna function. In a time where the natural world has become increasingly threatened, greater understanding can help strengthen conservation efforts.